The KIM-1 is the forerunner to the PET, the C64, and the VIC-20, and everything that came after, and they're actually quite rare. I blew up 3 of them today. Find out how and why, right here in Dave's Garage. Hey, I'm Dave. Welcome to my shop. I'm Dave Plummer, a retired operating systems engineer from Microsoft going back to the MS-DOS and Windows 95 days, and I just blew up some rather rare and expensive hardware that was and is near and dear to my heart. This is the story of why and how I fixed it. You see, a couple of years ago, I started searching for a collectible KIM-1 computer, since the KIM-1 is the first of the line of machines that became the Commodore PET and VIC-20 and C64 and so on. Those are the machines that I originally learned to code on, and so I really wanted a KIM just so that I could go back all the way to first principles. I searched for years to find the perfect specimen. If you're a longtime fan of the channel at all, then you may remember that I ultimately found it last year. A rare Revision A KIM-1, the OG of home computers. And better yet, the original owner had built it out as a full desktop system, complete with RAM boards and ROM boards and disk controllers and EEPROM burner and even a visual memory graphics display. It was in that episode where everything went wrong, although I didn't even know it at the time. You see, mistakes were made, as they say. The KIM-1 takes several different power supplies to run. In fact, it takes 4 different ones: a regulated 5-volt, a regulated 12-volt, an unregulated 8-volt, and an unregulated 16-volt. I power the KIM-1 separately, so technically it has yet another power input that makes it 5th. The boards in the stack use the unregulated voltages in order to be able to regulate their own 5 and 12 as needed on the individual boards, which can provide less noise than transmitting and distributing the power over the bus. Some boards, like the KIM-1 itself, do not have power regulation on board, and it's those that require the regulated voltages to be supplied. Now, as you can imagine, connecting multiple different power inputs could be a bit error-prone, especially when they're all using the same size barrel jacks. Rather than ordering a bunch of uniquely sized jacks, I simply color-coded with electrical tape to mark them in customary ketchup and mustard colors. For example, red for 5 volts and yellow for 12 volts. Then a stripe was added if it was unregulated. It was foolproof. Well, it was until I went to actually film that episode. At some point during the episode, it came time to connect the power, and rather than spin the entire stack around so that I could see the power plugs properly, I did it with the KIM-1 facing the camera for the best view. I'd connected the power lead so many times by that point that doing it was pretty much muscle memory anyway. I was sure I knew where each input went, but I was wrong. Very wrong. Somewhere along the way, I swapped the regulated 5 and the unregulated 16. That means that 5 volts was going where 16 volts was expected, but of course the converse was equally true, but worse. 16 volts was going where 5 volts was expected. And yet there was no obvious failure at first. I had no idea I'd even done it. The RAM started acting a little flaky, no doubt because the RAM boards require 12 volts and they were only getting 5. Unfortunately, they act very similar whether they're getting too little or too much voltage. I've been running my unregulated power just high enough to make the regulators happy, and sometimes it turned out to be a little too low. So just when you're thinking that plugging 16 volts of power into the 5-volt port is about the worst thing you can do, I upped the ante even further. I turned up the adjustment pot to increase the voltage a little bit to see if I could get the RAM working properly. And as soon as I turned the voltage up, that's when the magic smoke came out. I smelled it before I could even see it. Whereas the smell of napalm in the morning might be indicative of victory, the distinctive smell of electronics burning in the evening is most definitely a symptom of failure. I was devastated. Not only had I cooked a prized collectible, it was a result of my own failure, and one of the worst kinds of failure. The kind that results from being careless, or in my case, rushing through important steps to reach some desired end just a little faster. Years ago, I read a book called The Checklist Manifesto by Atul Gawande. In a nutshell, the book makes the case for extending the types of checklists used in aviation to other professions like medicine. It's a very interesting book that I'll include a link to in the video description, and had I followed its advice, I would have used a short 5 to 8 item checklist before booting up the KIM-1. Perhaps something like power supply off, cards physically seated and installed, address decoding harness connected to the KIM-1, Corsham I/O board plugged into the KIM-1 other port, serial port cable connected to the I/O board, power supply connections verified to color-coded ports, power supply on, press reset on the KIM-1. Simply following through and verifying each of those steps would have saved me an enormous amount of time and heartache. Now that it was too late, however, I was faced with the reality that my system was likely quite damaged and that I was a software guy with very limited hardware knowledge. And most of what I do know comes from watching YouTube channels like Adrian's Digital Basement and Yawn Beta. First, I had to determine what was actually damaged. To that end, I decided to connect just the KIM-1 and then add one board at a time and see what worked and what did not. The good news is that the rare KIM-1 itself was, so far, perfectly fine. I had separately powered it with its own 5-volt supply, and that appears to have protected it. The only thing I'm a little confused by is that pin A on the KIM's application connector appears to share the 5 volts on the bus. It's also present on pin 21 of the expansion connector. I thought perhaps they were diode protected so current could only flow out, but I didn't see anything like that on the board that would protect it. I'll just consider that one somewhere between random luck and divine intervention. If you have a theory as to why the KIM-1 was unaffected despite high voltages being present on the bus, please share it in the comments. I'm curious. My next step was to plug in the RAM expansion boards. I plugged them in one at a time, and at least the system still booted, somewhat of a positive sign. The first 16K memory board was supposed to map into memory at 2000 hex, but as soon as I went to that address, it acted just like ROM. I could tell it wasn't empty address space, or at least it was decoding the address bus. Curiously, as I experimented more, I discovered that the memory higher up, like at 5000, worked just fine. So it was only the first 4K that was missing. Now, if there's anything I've learned from watching Adrian, it's that you start with the basics. You check the voltages, the clock, the reset line, the address bus, the data bus, and so on. And so, that's where I started. With 4 banks of RAM on each card, but one row not working, I used a logic probe to walk down the pins on the non-working row of chips and compare them against the working set. Reminds me of back when I was 15, I managed to talk my way into a job as the repair tech at the actual Commodore dealer. I wish there had been a qualified tech there to learn from, but if there had been, they never would have hired me. I fixed mostly 1541 drives, C64s, and the occasional VIC-20. I soon discovered that some problems, like a defective SID chip or bad RAM chips, or even a faulty I/O chip, would have characteristic symptoms, and so those became easy to solve fairly quickly. But when a problem got gnarly, I didn't know anywhere near enough to sort things out from first principles, so my only real option was to take a scope with 2 leads, hook one up to a working machine and the other to the problematic unit. And then, through a slow process of elimination, figure out where it was that the 2 systems started to differ. Seeing where they diverged was usually enough for me to go on. Since I had 3 working rows of memory and 1 non-working, I followed that same age-old procedure. I took a logic probe and started to compare the signals between the pins on the working row of chips and on a non-working row. As I progressed down the pins, I soon discovered that the chip enable, or CE line, was a very active signal on the working rows, but it was always high on the dead row. All I had to do now was to work backwards to find out where things were the same, and then I'd be close to a solution. I traced the signal through the schematic and found that the square wave signal that alternates between the rows was indeed being generated just fine. For some reason, though, it wasn't making it to the 1 row of chips. That's when I found that the chip enable line trace had been cut at some point in the past, but I knew it had worked before, so how could that even be? Well, it turns out that the severed chip enable line is actually accompanied by a new resistor that was added to the back side of the board. My best guess is that this was a modification made by the previous owner, either in response to a service bulletin or perhaps just in pursuit of cooler RAM. My thinking is that the addition of the resistor allows it to still see a full 12-volt chip-enable signal, but without having to sink a whole lot of current. By limiting the current with the resistor, less heat needs to be dissipated by the RAM chips. That's just my theory. I have no idea if it's right. The results of testing the signal at the resistor made no sense to me, though. Measuring the resistor on the side furthest from the RAM chip, the signal going in there was just fine. But on the side closest to the RAM chip, it was always high, a full 12 volts. Well, how could that be? Again, I'm not a hardware guy, but even I was confident that a resistor shouldn't be able to modify the signal from a square wave into an always high signal. For one, it violates the laws of thermodynamics, and worse, it just made no sense. I decided I had to desolder the resistor and measure it out of circuit to see what the heck was really going on. As soon as I melted the solder on one side, though, something fell off the board. Not the resistor itself, just half the resistor. As near as I can tell, the resistor was fractured in the middle, but was held together by the solder that placed it into the circuit. Once it was free, the break was obvious. I have some doubts that a resistor would crack from being overvolted, but all I know for sure is that it happened at the same time. So whatever the reason, everything was obvious now except for one thing. How did the square wave become always high? I still don't truly know for sure. My best guess is that the RAM chips have an internal 12-volt pull-up such that when the pin is not connected low, the CE line goes high. It's one of those signals that is active low, and so perhaps the chip does that intentionally to stay turned off unless intentionally turned on. If you've got a good theory, that's another one I'd be interested to learn about in the comments. All I had to do, though, was to solder a fresh new resistor in its place, and sure enough, the RAM all suddenly worked perfectly. The second 16K RAM board had no problems whatsoever. It somehow dodged the many bullets I had thrown at it, and it worked perfectly as soon as it was powered up. So at least now I had 32K. The visible memory board, the really rare and hard part to find, was not as lucky. This is perhaps, as I said, the rarest of the boards because I can purchase a modern RAM expansion for the KIM-1 worst case if the RAM boards fail, but there's certainly nobody reproducing graphics boards for a KIM-1. It's also the only visible portion of the KIM-1 other than the LED digits, so it's rather important. It was also rather dead. There was no video being produced. The RAM was inaccessible, and in so short, it was a brick. The only good news was that the system still booted with it in place, so at least it wasn't dragging everything else down with it, but it was a long way from working. I have the original factory documentation for the board, and it actually contains a helpful page of electronics troubleshooting information. It helps to know a little bit about how the video signal is actually generated, though. My friend Rutger over in the Netherlands had recently sent me a copy of the Cheap Video Cookbook by Don Lancaster, and I'd been reading it, so I had a rough idea how a basic video circuit actually worked. And so, like the piano teacher who stays one chapter ahead of her students, I'll give you the basics as I understand them. As you may know, the original video standard was designed around CRTs that drew the picture line by line, left to right, top to bottom. Now that signal needs to include some sync information that tells the electron gun when to reset to the left side of the screen and when to start over at the top and on down again. To create those signals, the video board starts with a clock signal called the dot clock. That signal is then divided down several times so that there's a separate dot clock for the horizontal blanking signal and the vertical blanking signal as well. That's done on the graphics board by means of a clock crystal and a series of 74LS series logic chips that divide that clock. I could tell with my scope that the dot clocks were not running, but I could not figure out precisely why by poking around the circuit. There were a few chips that I suspected were bad, but even though I have a decent supply of simple logic chips, for many of the more obscure and older ones, I just didn't have replacements to experiment with. That's when I was struck by the odd thought that my old DigiPro EEPROM burner could test logic chips. I don't know where I got the notion from, but I loaded the software up and sure enough, there was a menu item there for testing chips. I sat down with the board and decided to test every chip on the board, basically in the order of most suspect to least. I tested the most likely offenders, and they were all bad. That seemed a bit unlikely, so I decided I should take the time to test all the chips on the board to get a better picture of what was going on. One by one, then, I carefully removed, tested, and replaced every chip that evaluated as good. All but 3 passed. And so I headed on down to my favorite local electronics shop called Vetco Electronics. We're super fortunate to have Vetco in our area. It's a literal electronics superstore, but think old school. Like the electronics aisle of an old Radio Shack and then multiply the selection by 10, and that's basically the store. As I'm fond of saying, they don't have a capacitor drawer, they have a capacitor aisle. I grabbed the chips I needed and headed home to swap them out. I popped in the new chips, installed the board, booted it up, and suddenly the dot clocks were running and the video was being generated. I was so close, and yet so far. That the board could display video now was a huge step forward, but as soon as I entered the board's memory address into the KIM-1 monitor, A000, I could see that most was not working really at all. The monitor is cool in that the LEDs show a continually updating value reflecting the memory's contents, but in my case it was just random garbage, as though it couldn't lock on to any single value. Attempting to store a value in the memory did nothing. When your only tool is a hammer, everything looks like a nail. Since I now had a little experience with the chip enable circuit, I decided to check those lines on the board as well. The chip enable signal tells the board which RAM chips to read from, and it alternates between the rows. That means I would expect 2 square waves that do not overlap. First it selects one row and then the next, and then it repeats indefinitely. What I found instead was a sawtooth pattern for one and basically noise on the other. Pretty clear even to me that at least one of them was wrong. Some foreshadowing. I was actually worried that neither signal was right, but for now it was time to back up to where the signals were generated and follow them through again, comparing one bank to the other and seeing where and why they diverged. Each signal is generated by a 74LS55 chip. I know from memory by now that it's pin 8 of U17 and U18. And on the scope, all was well. 2 square waves with pulses that didn't overlap, exactly as I had anticipated. Working forward through the schematic, the signal next progressed through a circuit that has a bunch of resistors and capacitors, and I have no idea what those were for. Their purpose is left to the reader as an exercise, as they say. But each signal then goes through a bank of 2 transistors. The final step seems to be amplifying the signal all the way up to 12 volts, and sure enough, the chip enable line on the 5580 RAM chips is indeed 12 volts, so it does make a modicum of sense. As far as I could reason, that really only left the transistors as potential problems, and so I first replaced the 2 transistors on the signal line that was producing the sawtooth pattern, and sure enough, I was now getting a tasty square wave on one bank. Unable to resist the temptation, I jumped into the KIM-1 monitor and promptly discovered that in the 2000 hex region, every second byte was now working perfectly. I was close enough I could taste it, Both RAM boards worked, the video generation was working, and every second byte of the video RAM was alive. Just one little problem left to go. Naturally, I replaced the other 2 transistors next, and to my surprise and dismay, there was no change. I fought with it for hours, and then for days, but I just couldn't find the problem. This whole deal is, again, complicated by my lack of experience in doing this kind of thing, along with the fact that this board has had significant modifications. There have been traces cut and components and jumper wires inserted both inline and on the back side of the PCB. My 3D visualization is pretty good, or so I thought, until I tried to keep the collector, base, and emitter pin straight in my head while flipping the board over and rotating it around, constantly trying to follow the circuit. These are ancient transistors, and since I couldn't find anything online to convince me that there were modern direct equivalents that I could use instead, I bought old NOS originals off eBay. And unlike modern transistors that have 3 pins in a row, collector, base, and emitter, these are in a triangle. Just as you could install a regular transistor backwards, these give you the opportunity to be off by 120 or 240 degrees as well. When I was all out of ideas, I found myself staring at the schematic over and over, hoping for some kind of epiphany. And that's when I saw my answer, right there on the schematic. Well, down in the corner, actually. Just a name, Chamberlain. Now, if anybody would know what the problem was, it would have to be this Chamberlain fellow who designed this circuit decades ago, right? If he were still alive, and if I could figure out his first name and where he lived and reach out to him and find him some 45 years later, maybe he could help me. And so, that's precisely what I did. Between Google and LinkedIn and various other tricks, I found a guy that I figured almost had to be him. He had the background I'd expect, had worked at places that made sense, and the name matched. It was even the right general area of the country where the board was actually made back in the mid-70s. I managed to locate an email address for him, and so I did what I've done any number of times in my life. I reached out to somebody unlikely. Now, Steve Jobs used to tell a story about being younger and reaching out to Bill Hewitt, one of the founders of HP, for a chip that he needed. If I recall the story correctly, Steve got not only the frequency counterpart he was looking for, but also a summer job. Bill was gracious, and Steve maintained in the story that, as he did all throughout his life, that if he politely and genuinely reached out to someone like that for a simple favor, he was very rarely turned away. My experience has been much the same, and this time was no different. Perhaps a week later, an email from Mr. Chamberlain awaited me in my inbox. He was indeed the engineer that had designed the board. To my great surprise, he said the entire effort, which had produced so many different MTU boards and products, was actually just a 2-person operation. Mr. Chamberlain gave me a ton of good ideas for general troubleshooting, and now that I had some more concrete information on what precisely my board was supposed to be doing, I updated him with everything you know up to this point as well. The punchline was that no matter what I tried, and despite replacing both transistors twice, the signal coming out of them was still garbage, but it was fine going in. And that's when he suggested something genius. At least it was to me, because of how long it would have taken me to figure it out on my own. What if the signal was being produced properly, he said, and always had been, but that some of the RAMs were receiving the CE signal and then pulling it down or otherwise corrupting it somehow? No matter how much power the transistors tried to use to shape the circuit, the RAMs could simply be grounding it out or otherwise wiping out the signal. All I had to do, he suggested, was to remove that bank of RAM and then test the signal to see if it got any better. And so, that's precisely what I did. I carefully removed each of the gold ceramic 5580 RAM chips and set them aside. Now, here's a little side story. When I was interviewing Albert Charpentier for the C64 Chip Designer episode, I was showing him around the shop via FaceTime with my iPad. I went to show him the KIM-1 and the MTU boards, and as I got kind of zoomed into the MTU memory boards, I heard him say, "Hey, those are my chips." He was also the designer of the RAM chips that are used on my expansion board. I connected the scope lines, and sure enough, with all the RAM removed from the problematic bank, the signal looked right on both. I had 2 square waves, perfectly amplified and staggered to alternate between the 2 rows of RAM. I swapped in a spare set of RAM that I was able to find on eBay and powered the system back up. Long story short, though, I was at a dead end. It still didn't work. I had to throw in the towel, so I emailed my friend Neil Breeden, who on occasion does repairs on my old vintage hardware. This problem was gnarly enough that he didn't want to tackle it himself, and he figured he needed a wizard, so he referred me to a fellow named Jonathan. He had his own KIM-1, so I shipped the video board off to him along with the chassis. Jonathan ultimately reported back that he had to replace a few faulty, sketchy sockets on the board, as well as 3 of the 4 chip-enabled transistors. He also did some other maintenance on the board, such as replacing several old capacitors and fixing up some physical construction on the back of the board that goes back probably to the 70s as well. It turns out that the one working transistor had provided me enough of a signal to make me think that one row was working, whereas both were actually still bad. So when I continually had been trying to get one to look like the other on the scope, I was never successful. Jonathan was able to locate, diagnose, and fix the problem from real knowledge and first principles, and I'm deeply indebted to him for his excellent work. I had one final big task that I wanted to accomplish, and that was drawing to the screen. I wanted to be able to draw lines and plot pixels and draw strings of text, none of which the KIM provides any code for. My first attempt at a line draw moire pattern worked pretty well, but only on the top half of the screen. That would later turn out to be a bug or limitation of the compiler I was using and its ability to index off a base pointer. So once I did the math more manually, broken up over several steps, I was able to get it to draw properly onto the full screen. So now that I had simple Brazenham line draw working, I moved on to text. I grabbed a ROM font from a website that was public domain and wrote the routines that were needed to render a character onto the screen, advance the cursor, go back and down, and so on. The text came out backwards. That's because on the MTU visible memory board, the bytes in screen memory are arranged left to right, as you'd expect, but the bits within a byte are swapped and arranged right to left, so it's a little bit odd. I added an initialized font call that I wrote in order to reverse the bits of the font bytes, and then everything rendered appropriately. And with that, I'd reached the milestone that I was aiming for, graphics and text on the MTU visible memory board. So I just realized in editing that I never did explain blowing up multiple KIMs. Rest assured, 2 of them were my replica KIM that stands in for the real KIM when I'm experimenting, and it was pretty easy to fix. It was a 7404 one time and a 7400 the other time. The next time was a little more troubling because it was on a Rev G KIM-1 that I had put in when I was confident things were working, but unfortunately they were not yet, and it also suffered a fate, but it's not socketed, so I've got to order a chip and a socket. In any event, what caused all of this is the fact that this is now a bus system. So you can imagine there's a male KIM-1, and this blue card here, the short card, is also a female card. So how do I plug a female card into a female slot? Well, I made a gender changer board. And as you can see, it was a routing nightmare for a fellow in Spain who helped me out with that aspect of it. The one mistake I made was to not leave any flashing on the edges, so it's easy to miss a line. That wound up having some of the port or pins be wrong, and that was the failure of the KIM-1s. The KIM-1 full stack is up and running again. Well, almost. It runs as well as it has for a long time, but I don't have an 8-inch floppy drive to test the floppy controller with. And some of the video RAM never did pass the RAM test until Jonathan replaced chips, so I got to double check those as well. Now, if you happen to have an 8-inch Shugart or compatible floppy that you'd like to part with, please let me know. One important caveat, however, is that I'm looking for a known good unit so that I don't have to troubleshoot the drive and the software at the same time. Lastly, and this is a real long shot, I'm looking for a copy of the CODOS software that's shipped from MTU. It doesn't seem to have been archived anywhere, so if you somehow have digital access to a copy of any of the MTU software, be it their extended basic or the CODOS operating system or similar, please reach out to me. If along the way you found today's episode to be any combination of entertaining or informative, I'd be honored if you consider leaving a like and subscribing to my channel. If you have any interest in matters related to autism, Asperger's, or ASD, please check out my book on Amazon, Secrets of the Autistic Millionaire. It's got nothing to do with money and everything to do with living a successful life on the spectrum. It's everything I know now that I wish I'd known back then. Remember, I'm mostly in this for the subs and likes, so please be sure to leave me one of each before you go today. In the meantime and in between time, I hope to see you next time, right here in Dave's Garage.